As the title indicates, we're going to be looking at inverse trigonometric values in this video. You should have the class notes and example sheet for section 7.8 with you, and just turn it over to the back. We're going to pick up doing some practice with inverse trig functions. What we defined on the first part of the sheet was the fact that the output values for 3 of the inverse trig functions, let me get my marker, that would be arcsine, arccosecant, and arctangent. Their output values always go from negative pi over 2 to positive pi over 2 for the angles. All right, so you're thinking in terms of the fourth quadrant and the first quadrant. All right, and then the other 3, the arccosine, and naturally the arcsecant, they're kind of related, and the arccotangent, their output values always go from 0 to pi radians in terms of their angles. All right, and you can see that all of them do involve the first quadrant, right? Anytime you have a positive input for one of these inverse trig functions, the output will come from the first quadrant. It has to, all right? You'll also notice none of the outputs are in the third quadrant, so no inputs that you can put into an inverse trig function will yield an output from the third quadrant. So these 3 here, if they have a negative input, will yield an angle between negative pi over 2 and 0. And then these 3 inverse trig functions, if they have a negative input, will yield an output or an angle from pi over 2 all the way to pi in the second quadrant. Okay, so you can use this diagram to help you when you're trying to figure out what angle you need to give for an answer. And let's get started here with the arcsine of 1/2. I'll remind you that the sine of an angle always equals a ratio, right? So we're turning it around, and we take the inverse sine of a ratio to equal an angle. So this 1/2 right here is a ratio, right? I'm going to put an R right there, and we are looking for an angle. All right, so since, of course, we have a positive input here, that makes it easy. We know we're looking in the first quadrant, and this is one of our exact values, so we just got to think, where is the sine going to be 1/2? If it helps, you could write this as, you could write, we're looking for theta, and you know that the sine of theta is equal to 1/2. All right. The important point to remember is that our answer here, there's only one answer. We can't give 2 answers. And so the only answer we can give is pi over 6, even though the sine of 5 pi over 6 out here is also 1/2. Okay, that can't be the answer because we have to give our answer between negative pi over 2 and positive pi over 2 when it's inverse sine. All right, it's the same thing as if we were talking about, hey, what's the square root of 9? Okay, if I ask what's the square root of 9, the only answer you can give is 3. The square root of 9 does not equal negative 3, even though negative 3 squared is 9. Okay, because of the way we've defined this inverse sine to be a function. All right, so why don't you give number 2 a try? Pause the video and see what you think the single answer is for the inverse sine of negative 1/2. See if this is what you got. Now, if you said 11 pi over 6 here for your answer, you were thinking correctly because you were thinking fourth quadrant. You're looking for, the angle whose sine will be negative 1/2. But 11 pi over 6 is not exactly right because that number, 11 pi over 6, is not between negative pi over 2 and positive pi over 2. So we have to use negative pi over 6. This is the only answer that's correct. All right. We obviously don't want to use 7 pi over 6 because that is in the third quadrant. Since we're not in the classroom, I'm not giving you too many of the inverse secants or cosecants or cotangents, but here's one. Let's go ahead and see how we would do this. All right. once again, let me mark the 2, right? We know the 2 is a ratio, and we know we're getting back an angle, right? So if it helps, you might want to just think, all right, so we're looking for an angle where the secant of that angle is 2, all right? And if you're me, I don't like to be thinking in terms of secant. I'm much more comfortable with sine or cosine, so I would change this to cosine of theta is equal to 1/2, right? We can just take the reciprocal of 2, and we know what that's the cosine. All right, so once again, we have a positive angle. Let me get there. So we have a positive, sorry, not a positive angle, but a positive ratio. So we do know we're going to be looking once again in the first quadrant for the angle whose cosine is 1/2. And I think I know that that is going to be, whoops, get my pen back here, that our theta is going to have to equal pi over 3. All right, that's the only answer. Even though there is another place where the secant is 2 or the cosine is 1/2, that would be down here in, let's see, cosine being 1/2 would be down here at like 5 pi over 3 or negative pi over 3, but that can't be the answer. All right, why don't you give number 4 a try, pause the video, and see what you come up with, given that you've got, it is a inverse cosine, but you got that negative. All right, did you get this? Since our input is negative, we know, and we're looking inverse cosine, we know we need to be looking between 0 and pi over here, and the negative would mean we're going to be in the second quadrant, right? We can't be in the first quadrant if we have a negative input, so it must be in the second. And nice thing is, when it's a root 2 over 2, we know it's one of the pi over 4s, and that would be 3 pi over 4 here. All right, hopefully you're getting these right. Let's keep moving. I think the tangents and the cotangents tend to be a little harder. Recognizing these numbers may not be quite as easy as when it's sine and cosine. But, as soon as we see a root 3, we know that we're not dealing with a pi over 4 angle. It must be one of the others, either over 6 or over 3. And so with that root 3, we just got to think, we're dealing with root 3 over 2 and 1/2. So how can we get a root 3, on top? This is basically root 3, root 3 over 1. So how can we end up with that? And just kind of off to the side, you just got to ask yourself, would that be root 3 over 2 divided by 1/2? Oops, sorry, divided by 1/2? Or would that be, 1/2, I'll come over here, divided by root 3 over 2? And hopefully you've done enough of this fractions divided by fractions to realize that, or to know that we are talking about this case when the root 3 is on top, right? We're just going to flip that 1/2. It'll be a 2 times this. The 2's will cancel. You'll be left with root 3. So we're looking at the top part being root 3 over 2, and we know that that would be sine, okay? So you can think of it this way, right? We're looking for the sine. Here, we could write this in here. We're looking for an angle where the sine of theta, right? Sine of theta, in this case, is the root 3 over 2. Now, whether that's positive or negative, that's something we have to kind of think about. But let's see, with inverse tangent being negative, we know that has to fall somewhere between negative pi over 2 and positive pi over 2, right? So we must be looking in the fourth quadrant, which would mean our sine is negative, right? Not our cosine. So that's a way we can think of it. Where is the sine going to be negative root 3 over 2? And thinking about that, that's the longer piece is going to be the y, and so that would be the 5 pi over 3, I believe, right? We have a winner. So the inverse tangent of negative root 3 over 1 would be 5 pi over 3, right? Oh, wait a minute. I think I fell into the trap, right? If we look closely at our range, we got to be going between negative pi over 2 and 0. So even though we found the right location here in the fourth quadrant. We can't use 5 pi over 3 because that number is not between negative pi over 2 and 0. So we're going to have to go with, instead of 5 pi over 3, we're going to have to go with negative pi over 3. That is really what can be unnerving about these problems, is you're even in the right spot, but you just don't quite have the right number. Okay, why don't you give number 6 a try, the inverse cotangent. So I'm throwing a cotangent at you. Pause the video and see if you can get this answer. Great job if you said 5 pi over 6. Right now, it's still the root 3 over 2 over 1/2, but now that's the x part, right? The cosine. So we're looking for where the cosine is root 3 over 2. And in this case, since our input is negative, we know we need to be looking between 0 and pi, and negative means we must be in the second quadrant. So I believe that would mean our x's are negative, so the cosine would be negative root 3 over 2. And that's going to be happening over here, 5 pi over 6. All right, let's move on. Keeping in mind that sines and arcsines are inverses of each other, hopefully many of you are looking at this one and thinking this one's rather easy. What's the sine of the arcsine root 2 over 2, right? Keeping in mind root 2 over 2, that's your ratio, right? So when you take its arcsine, this is your angle theta, and now we just want to turn around and take the sine of theta, right? We'd better get root 2 over 2. If we want to even think about what theta is, I believe it would be pi over 4. The sine of pi over 4 is root 2 over 2. All right, so you might look at number 8 and just assume, well, the arcsine and the sine basically are going to cancel each other out. So if that's the case, then our answer must be 5 pi over 4 over here, okay? But this is where you really have to be careful, because one thing we might think about is, where is 5 pi over 4? That is over here in the third quadrant. And we know that there's no way that our output for an arcsine can be in the third quadrant. So 5 pi over 4 is actually not correct. All right, see if you can figure out what angle we should get back for this arcsine. Pause the video and give it a shot. All right, let's walk ourselves through it now. The sine of 5 pi over 4, I'm going to change colors here. The sine of 5 pi over 4, that's down here, of course, in the third quadrant. That's going to be negative root 2 over 2. Okay, so now we're asking ourselves, what's the arcsine of negative root 2 over 2? And arcsine, right, we know has to go somewhere between negative pi over 2 and positive pi over 2. So we can't be giving back 5 pi over 4, and where we're going to be negative would be in the fourth quadrant, right? So we should be looking right here in the fourth quadrant. Now, remember, you might be thinking, oh, that's 7 pi over 4 for the answer, but no, we need to make sure our number is between negative pi over 2 and 0, so we have to go with negative pi over 4 for our answer. If you said negative pi over 4, great job. For the last two problems on the sheet, you might be thinking, oh, I need my calculator for this, because that 4/3 is definitely not something that we're used to seeing on the unit circle. However, because this number is given to us exactly, we can actually get an exact answer for the sine of the inverse cotangent of this number without a calculator. In fact, you guys have actually already done this problem. Hard to believe, but you have done a problem very similar to this. Let's think about this, okay? What is that 4/3? Is that an angle or is that a ratio? Okay. Yes, we take the inverse cotangent of a ratio, right? And we get back an angle. Let's call that angle theta. So the inverse cotangent of 4/3 is theta, and this problem is asking you, hey, what's the sine of theta, okay, sine of theta equals what if you know that the cotangent of theta, right, is 4/3, all right? And one more thing you also know is you know what quadrant theta is in, okay? By virtue of the fact that the inverse cotangent here is the input for the inverse cotangent is a positive number, you know that theta has to be in the first quadrant. So there's a lot of information packed into this one little statement right here. And so hopefully you recognize this problem now. We actually have two methods of doing it. You could use some of the Pythagorean identity, or if you're like me, I would be thinking x, y, and r and before I use Pythagorean. Why don't you see if you can finish this problem to figure out what the sine of the inverse cotangent of 4/3 is. Pause the video and do that. All right, I'll be impressed if this is what you got. Did you get 3/5? Let's see, here's how I would do it. I know cotangent is x over y, so I know the x and the y. I just need to figure out the r, right? The x is going to be 4, the y is going to be 3. Keep in mind, I am not on the unit circle, but I do know that r squared is equal to x squared plus y squared. All right, so of course we know by now, probably this is the 3, 4, 5 right triangle, right? 16 plus 9 is going to give us 25. So we can figure out that r is equal to 5. And now if I want the sine of theta, I just take my y, which is 3, and I put it over my r, which is 5. All right. Want to give you a shot at one more of these. If you want to, let's take a look at the last page here. So hopefully you're already thinking, I mean, when you look at the information, it's almost the same as what you saw before. The only difference, right, is this negative here. So you know the answer's got to be a 3 over a 5. Question is it going to be negative or is it going to be positive? So why don't you pause the video and see if you can figure that out. You may have been tempted to add a negative to your answer, but if you didn't do that, then you are correct, right? So inverse cotangent with a negative input, right? That's the ratio. Its angle is going to have to be in the second quadrant. And if we're looking for the sine of that angle, right? This is just theta. We're looking for the sine of theta. Well, the sine of theta in the second quadrant is always positive. So our answer remains 3/5. Same answer as what we got on the last one. Okay, so hopefully you're feeling a little stronger about evaluating inverse trig functions, keeping in mind that the input is a ratio and you are looking for an angle for the output, but you got to find, what's the correct angle. There's an infinite number of angles that give you a certain ratio, but you've got to make sure you find the correct one, because there's only one possible answer when you're dealing, or one possible output when you're dealing with a function.